Thank you very much. It's a true pleasure to be here and to talk about work that I've been doing for a few years now. So, this work is in collaboration with these people at the very least. It started off while I was a PhD student at Harvard, so with my advisor Vahid Tarok, as well as all these other collaborators while at Harvard. And then when I moved to University of Illinois at Chicago about a year ago, started working with my colleague Daniela Tuninetti and our joint student Stefano Rini on this same problem. But we've really progressed a lot in the past year. So I'm going to be using basically my PhD topic, but we've really made a lot of progress in the last year, and that's what I'm going to be highlighting in this talk. Okay. So the story starts off with, I want to compute the fundamental limits of how fast can I efficiently, reliably communicate, and this is all, of course, in the information theoretic sense, meaning probabilities of error going to zero as block length or delay can go to infinity. So this is a well-studied problem for the point-to-point channel. This is our first piece of the pie. Here we have one sender, one receiver. Capacity of this simple point-to-point channel is well known. It's given by the capacity is the mutual information between the input to this channel and the output to the channel. The input being what this guy sends, the output being what this guy receives. Great. So the next step towards understanding fundamental limits of all sorts of networks is to put multiple antennas at all transmitters and receivers. Why would we do this? One of the driving scenarios is in wireless communications, where the channel will fade over time and will become strong and weak. And so one hopes to add in some redundancy and some diversity by introducing many antennas at the transmitters and receivers. In some sense, it's unlikely that all of these channels will fade simultaneously. And so the hope is to have some kind of diversity multiplexing trade-off in this regime. So we understand pretty much how to communicate over MIMO channels, multiple input, multiple output channels, from an information theoretic perspective. Next step towards our grander understanding of communicating over networks is to try to distribute these antennas. So now I have multiple transmitters here, multiple receivers, which are spatially separated, i.e. these you can think of them as two antennas, but they are no longer co-located, so you can no longer put the same information on them at the same time. So you have to sort of take into account the overhead needed for those two transmitters to cooperate. So essentially this is becoming a distributed MIMO kind of system, or a multi-user information theory kind of system, where you have multiple transmitters, multiple receivers, which are interfering. And the question I want to look at is, what are the fundamental limits of this network, meaning at what rates can all of these users simultaneously transmit and receive? Okay, but this is sort of an unknown area. There's a lot of active research in this type of small networks, where we only have a few users with links, but the capacities of all these types of networks are still, some are known, some are unknown. The one I drew here, interference channel, capacity is still unknown in general. But there has been a lot of recent progress. But the biggest picture here is what we'd like to solve is the capacity of a wireless network, or capacity of a network in general, where you have multiple arbitrary transmitters, arbitrary receivers communicating in an arbitrary setting, arbitrary channel. So this, I think we're very far from understanding this, in part because of its complexity, but we do have a few manageable measures, such as scaling laws of such networks, that we have to sort of understand the fundamental limits of communication in such a network. So what I'm looking at is not only this type of scenario, but with cognition. And so what do I mean with cognition? It can mean a whole bunch of things. What I'm going to take it to mean, or this is sort of the term we introduced, is information theory inspired by cognitive radios. And what are cognitive radios? So to me, radio is just a wireless link. It's no AM radio, nothing like this. It's a wireless link, source, modulator. There's my wireless channel. Should have put wireless. And, you know, all sorts of stuff. Cell phones, satellites, Wi-Fi, whatever. This is radio to me. Software-defined radio takes the modulator and demodulator, which is usually or traditionally being implemented in hardware, and says, rather than do it in hardware, let's do it in software. So get as close to the antenna as possible using software. This is beautiful for a theory person like me because I could never design stuff like this, but I could probably write up a little bit of code to implement some kind of new communication strategy that I'm thinking of. Okay, next step is a cognitive radio, which is a software-defined radio with some added capabilities. So it's a software-defined radio, but that now is becoming cognitive. And what does this cognitive mean? I've put chameleons as the image because what they are is essentially wireless devices that sense their environment and adapt to it. So these ones have a sort of closed loop information processing unit in there. And the idea is that they're smart not only because they can be programmed in software, but because they have this ability to sense and transmit. It's, you know, the difference between cognitive and software-defined radio is marginal, but for us, I take it to mean a smart wireless device, okay, that can do things that regular traditional wireless devices cannot do. Okay, so this is one example of a software-defined radio, cognitive radio. It's the famous GNU radio software combined with the USRP hardware, which you can very easily buy. We bought some. This is taken from our lab at UIC. Okay, so back to my own problem. I want to solve fundamental limits, okay, on cognitive networks. So networks where we have some of the nodes being cognitive radios. Okay. The big question is how to model them. So when I say fundamental limits, what I mean is capacity regions. And I'll talk about what this means to me. And so here, channel capacity, the most basic notions. So I have a sender that I'm always going to denote with X's, and my receivers are always going to be Y. And the foundation of information theory is built on the fact that you can probabilistically model communication. So you model a channel as a set of conditional distributions P of Y given X. How does your output relate to your input? Okay. Capacity of this point-to-point channel is the maximum overall input distributions of the mutual information. This is this I term between the input and the output. And this is in bits per channel use if you take this mutual information to be log-based too. So why is it a maximum overall input distributions? Because that's what I get to pick, right? You get to pick how you're going to transmit such that this quantity here is maximized. Let's just have a look at the mutual information and see how it could make sense. Worst case scenario, when can you not communicate? When the output and the input are completely independent, i.e. when this product distribution here will break down as this joint distribution will break down as two product distributions, this log will become 0. And so you would expect no information can be transferred if the input and the output of this channel are independent. So this is just sort of a sanity check. And for the rest, I take it that you can believe that this is, in fact, the capacity as proved by Shannon. So it corresponds to the highest rate in bits per channel use that you can communicate at reliably. And so basically what it says is, for all rates, I'm going to be denoting rates by R. Rates is how fast I can communicate. Below capacity, great. Reliable communication is possible, meaning probability of error goes to 0 as the number of channel uses goes to infinity or as the delay goes to infinity. And for all things above capacity, all rates above capacity, you can prove that the probability of error is bounded away from 0. Example of a capacity of a wireless channel. Simple point-to-point channel with some fading and Gaussian noise capacity. In this case, the input distribution that maximizes the mutual information will be the Gaussian distribution itself. And so this is shown just by Gaussian maximizes entropy type of properties under a second moment constraint. And your capacity will turn into this famous formula, half log 1 plus SNR. Okay, great. I'm just putting this on because I'll be using it a bit later on. Okay, so capacity is just a number in general in a point-to-point channel. But in multi-user information theory, we deal with multiple streams of information. And so capacity becomes capacity regions. So it's just the multidimensional version of capacity. And so here, take this example of a multi-user network. 2 transmitters, 2 receivers, 2 rates. X1 wants to talk to Y1, X2 to Y2. this would be a capacity region, would be all the sets of rates at which you can reliably communicate both of them simultaneously. Okay? And then outside the capacity region, nope, you cannot communicate reliably at those rates. Okay, capacity regions are in general very hard to find. Only in certain multi-user channels are they known. So what we content ourselves with sometimes is finding outer bounds to such regions and achievable rate regions. I'm going to be talking about achievable rate regions. What these regions are sets of rates for which you can prove that the probability of error goes to 0 as n goes to infinity. But that's not to say that those are the best rates you can achieve. Okay? So they say, yes, we can achieve these rates, but it could be that I can think of a better scheme later on for which I can prove higher rates can be achieved. The capacity region is then the set of the largest achievable rates that you can show. Okay. So cognitive networks. So the fundamental limits part that I'm talking about is capacity regions. This is what I'm after. And cognitive networks part, what's the motivation for this? One is this newfound cognitive radio that has sort of popped up. Right? Technology has advanced enough for us to be able to program wireless devices and have them do smart things. The other motivation is spectral efficiency. So simultaneously, when these cognitive radios sort of came on the scene, these ideas of secondary spectrum licensing showed up. So here I'm showing the United States frequency allocation chart, which just says basically all the frequencies over which radio communication is relevant has been chopped up into all these different licenses. So the FCC has said, you get the right to this chunk, you get the right to this chunk. And as you can see, it's sort of, all these different colors are different uses, and it's sort of full, right? All this spectrum has been divided up and given out. So the idea is that they're not being very well used, these different spectrum chunks. So the idea is that in the future, we'll have this kind of secondary spectrum licensing idea where you will have primary license holders, the ones that are like Verizon right now that have control of a certain license or a certain frequency band. But then you will have these opportunistic blue circles, which are called secondary users, that will opportunistically transmit over the same band as these gray users, the primary license holders, subject to certain constraints. So you're not always going to want to allow some other user to use your band. They're going to have to be smart about it. And so the idea is that these secondary users would be cognitive radios. Okay, they would have some kind of sensing mechanism, and they would be able to sense when the primary users aren't transmitting or when they are. And the real question I want to ask is, what can we do, with these cognitive radios? What kind of limits of this channel exist when you have these primary users who sort of have more right to the channel, and you have these secondary users that are showing up and wanting to use it opportunistically? Okay, so the scenario we're looking at is where we have a primary link, they're always going to be the gray circles, and where we have a secondary link that you can think of as a smart cognitive link. Okay, these devices are cognitive radios. If they transmit simultaneously, they will interfere. So that I'm dealing with wireless channels or any sort of channel where there is interference between the two. If they don't interfere, then everything is fine. There is no problem. So my question is, what can the cognitive link do? So the problem essentially at first boils down to, how do I model cognition? Cognition can be modeled in many ways, and this is a debate. It's something personal. You can say, cognitive radio can do this, can do that, whatever you want. So basically, the assumptions on the primary and secondary models will dictate the behavior and performance of the system. This is very intuitive, but I want to quantify how much. Right? Cognition boils down to side information and how to use it, and that's hopefully what will become clear to you. That's basically how we're going to model cognition. How much side information these ones have about this guy's transmission. And by side information, I mean extra information that you can use to achieve better communication. Okay, and I'm going to use information theory to tell us which of the techniques and which of these different assumptions are most promising. Most promising from a rate perspective, from a capacity region perspective. Okay, first thing, let's start thinking about what we can do when we have this cognitive link that wants to transmit simultaneously with this primary link. First thing he could do is he could sense, using his cognitive abilities, the channel, and look at what time and frequency the primary is transmitting. And if he's able to perfectly sense that, he can go and transmit in the white spaces, the spectral holes, as it's called in the literature, right? These white space filling devices. If you do this, what is the ideal capacity region of such a system? Capacity regions now are going to be two-dimensional regions. R1 is the rate of the primary user. R2 is the rate of the secondary user. And so here, it's easy to see this will just amount to a time-sharing solution, right? A user 1 is his maximum capacity is mutual information x1, y1. This is when user 1 is transmitting the whole time. This is when the other guy is transmitting the whole time. And so this whole triangle here is what's achievable. What's the side information needed? You need the secondary user to be able to perfectly detect when this guy is transmitting. Okay, and when he's not transmitting, go. Second idea, he could just transmit. Forget sensing whether the primary user exists. Just transmit. What happens then? The two users interfere with each other. Fine. What's the capacity region then? Well, this is not the capacity region then, because the capacity is in general unknown, but an achievable rate region would be that each user here treats the other interfering link as noise. Then, if we're in a Gaussian channel, all these things that I'm plotting are just for Gaussian channels because they're computable then. The rate would be half log 1 plus the signal to interference plus noise ratio. So this means that this receiver, for example, is treating the interference from signal 2 as noise, which is, of course, decreasing your achievable rate. So this is the region that you get then. This, I'm letting the secondary user go from power 0 to power P2, and this will get you along this line, basically. If this guy's transmitting at power 0, then this guy's not going to have any rate hit, right? He's not going to see any interference. So you'll be at that point, and as you increase the power, you'll go up there. This is related to an interference temperature idea that we've seen in the literature, where the interference temperature is how much noise is being generated at this user from this cognitive transmitter. And basically, if you know what kind of interference he can deal with, then you can adjust your power to sort of fill in that interference. So that's how it relates to that literature of the interference temperature. Side information needed is how much interference you cause this guy. So you need to know this channel, basically, as well as his interference level currently. Next, more intelligent thing you can do is you can do opportunistic or cognitive decoding. What this means is this is the message of the primary user, this link. And what this guy can do is if he has the code books of this one, i.e. if he knows how to decode the primary user's message, he could decode this one if this channel is very strong. Strip it off your signal, and then have a clean channel for your own transmission. So this is just an example of multi-user decoding. Side information needed. This guy needs to know this guy's code book. All right, great. Bigger region shows up. Next, fourth most intelligent thing to do. Always, you notice that my assumptions on the side information are always getting stronger and stronger, but my region is growing. This is the problem that I'm going to be talking about for the rest of the talk, which is simultaneous cognitive transmission. So here we model cognition in the fully idealistic and perhaps unrealistic even sense that transmitter 2 has the message that transmitter 1 is going to send. Okay? That's what this green link here means, is non-causal, a priori, all this message knowledge of user 1's message at transmitter 2. Okay. Why would this be possible? Well, this would be possible if this guy is, this link here between the primary and the secondary is much better, and then in a fraction of the time this guy could get his message. This is I'm showing an example of a causal way in which you could get the message, but we're idealizing it to mean that this is non-causal, meaning this channel here would have infinite capacity. Another way in which it might be a reasonable assumption is if the primary transmits a message, not successful, this one gets asks for a retransmission, then in the second retransmission phase, this might be a reasonable assumption if he had overheard it in the first phase.
Natasha,
yeah.
X2 knows the code book of X1 or knows exactly
the message index,
so
as well as the code book.
Yeah. So actually it looks like X1 and X2 are almost in the same place.
Almost, except that it's asymmetric. And that actually plays in. But yeah, it does look like that from one of the messages' point of view. It looks like a MIMO. Yeah. OK, so this channel model, this one right here, relates to many of classical information theoretic channel models. First one is interference channel. Interference channel, 2 independent transmitters, 2 independent receivers that transmit. And this is sort of called the competitive mode of operation, where these guys are essentially competing for the channel. They both want to get their own message across. The capacity of this channel is still unknown in general, but the most recent results have been within 1 bit kind of results. So we know capacity to within 1 bit in the Gaussian noise interference channel. It's a recent, quite strong result. But in discrete memoryless channels, still wide open. It also relates, if this was a 2-way arrow, like, to the 2 transmit antenna broadcast channel. So you could envision these 2 transmitters being 1 transmitter with 2 antennas transmitting to 2 different users, which would be the 2 transmit antenna broadcast channel. Discrete memoryless channel capacity is still unknown, but recently the MIMO Gaussian broadcast channel capacity was computed. And so this would be a kind of cooperative behavior, meaning that the 2 transmitters would fully cooperate to transmit the 2 messages. Right? So you would expect larger rate regions in this case. So we have something that's in between these 2. And it's interesting because I think it's the first example of this highly asymmetric kind of cooperation between the transmitters. And surprisingly, it had never been looked at before. So this is what we're calling the cognitive channel, meaning that this one has non-causal, asymmetric side information about X1's message. And so I ask what rates are achievable. And these rates are achievable, this big black region here. The interesting point is, for the first time, we're moving away from this single point-to-point link for user 1. Why is this important? It's important from a motivational perspective. What is rate 1? Rate 1 is the rate of the primary user. So for the first time, we're increasing the rate of the primary user, making it sort of in his best interest to want to adopt such a scheme. Okay, and of course, user 2 is also experiencing great rates. This is at the cost of a lot extra side information, right? This possibly unrealistic side information, but which is an acute problem nonetheless. So at this point, the rest of the talk is sort of going to be more information theoretic, less story-like. And I'm just going to try to abstract that last channel model that we were talking about and see how we can achieve that big black region. Right? OK, so here we start off. It looks kind of like the interference channel. Right? The interference channel has 2 transmitters independent, 2 independent receivers. And so you have the channel modeled by a set of conditional distributions. So here notice that what the transmitter 1 sends is X1, which I'm just showing depends only on message 1. X2 depends only on message 2 because there's no cognitive message knowledge anywhere. OK. So here is our discrete memoryless cognitive interference channel. I'm writing discrete memoryless because that's the first channel model that we sort of attacked, where input and output distributions come from discrete alphabets. So here, this is our cognition link here. I'm sorry, it's not consistent with the previous stuff. This is our new stuff. So here, this one will be the cognitive link, the top, the 1s, and the 2s will be the primary users. Okay. What we're also interested more generally is the Gaussian cognitive interference channel. So this is when this distribution here looks like an additive Gaussian noise channel. So you see that what you receive is what you transmit plus something on the interference link plus some N1, where this N1 is going to be Gaussian noise. Okay. So this is in general what we're after. This is easier to visualize and often easier to compute the rate regions. Okay, This channel model was all introduced pretty much in 2005, and this is what I basically wrote my dissertation on. Since then, capacity has been discovered in very weak interference. So these are all conditions on these A and B links here, right? And conditions on this channel distribution. So for certain channel distributions that satisfy certain conditions, you can show capacity in weak interference and very strong interference. People improved the region shown here in 2008 with a larger region. At some point, we realized that there's a broadcast channel actually contained here, which none of these previous regions had ever noticed somehow. New regions were computed. This is very recently. And the interference channel with the cognitive relay. All of these sort of relate to this cognitive channel that we were talking about. This idea of cognition has also taken, been looked at from a broader sense. So people have looked at causal cognitive interference channels, where this message knowledge is no longer assumed to be perfect and a priori, but learned on the fly. Semi-deterministic cognitive interference channels, where part of the links are non-random. Cognitive interference channels with secrecy, people have looked at. Cognitive Z interference channel, where you only have one of the links interfering, the other one clean. Degrees of freedom, I'll be talking a bit about that later. Wiener-type cognitive interference networks, where you have a whole string of them, so you sort of put these networks to infinity. Interference channel with the cognitive relay, this is also something we've worked on recently. These are all sort of generalizations or extensions of this idea of cognition to other scenarios. And the basic idea is that cognition in an information theory in our community has sort of been equated with non-causal side information at part of the transmitters or part of the receivers. And so this can lead to a whole string of new results. What if you put a bit of side information here, a bit of side information here? What kind of rates do you get? Where do you want to introduce that side information to get the maximum capacity regions? So our contributions recently, and this is what I'll be presenting next week actually in Zurich, we derived a new region that contains all of them, basically. And what is interesting is that so far nobody had ever been able to show inclusion of the original region shown here, and we were able to do that recently. The other thing that I'm going to be talking about is that in Gaussian noise, we have a constant bit result for the first time. What this means is that we've found a region that in Gaussian noise always lies within 1.87 bits from the outer bound. This is in the spirit of this one-bit result of David Say for the interference channel. Okay, and then we have capacity in certain new cases and channels, but in general, we don't have the capacity region. Okay, we have a constant gap result, and we have certain new channels. But we have capacity in some interesting channels. For example, the high SNR deterministic channel, which has also received a lot of attention lately. So what's the basis of my achievable scheme? Basis of my achievable scheme is fairly classical. Okay, it involves rate splitting, superposition coding, and Gelfand-Pinsker binning. And I'll talk about each of these ones briefly. So what's the idea behind rate splitting? Rate splitting says I have this rate that from transmitter 1 to receiver 1, transmitter 2 to receiver 2, and I split it into different components.
So R2 is the primary now, yeah?
R2 is the primary now. Okay. R1 is secondary. So what are these different notation? What I mean is that W2 is the message of the primary gets split into 3 parts. Okay, and the message of the cognitive gets split into 2 parts. And what are these indices supposed to mean? 2 just comes from user 2, 1 comes from user 1. C means common. C means common. What does this mean? It means that U2C encodes part of the message of W2, and this part of the message is going to want to be decoded both at receiver 2 and receiver 1. That's why I'm calling it common. Okay, even though receiver 1 doesn't care about decoding the message of user 2, it is beneficial from a rate perspective to sometimes decode a part of it so that you can subtract it off your received signal and clean up the channel for the rest of it. So that's the main idea behind why you would want a rate split. It says, rather than treating everything as interference, rate split, treat part of it as interference and part of it as noise. Part of it as interference and part of it as, treat it as a desired signal so that you can decode it, subtract it off, and thereby improve your own transmission rates. So the art lies in how much information should I put common and how much should I put non-common. Okay, so this is what these two C's mean and what the 1C means. 1C is the part of message of transmitter 1 that wants to be decoded both at receiver 1 and receiver 2. 2PA is from user 2 that's private and that is sent alone. So 2PA sent alone means he's going to send it, but he will not send it at all. So alone will make more sense when I talk about B here. The B means broadcast. So this is a part of the message from user 2 that is broadcast actually by transmitter 1. Again, why is this possible? Because of this asymmetric side information, this link there. Transmitter 2 knows the message of transmitter 1 knows the message of user 2, so is able to do anything with these messages that he wants. Okay, and one thing that he can do is he can broadcast it. Okay, and here, this is the part of message 1 that is broadcast. So it's basically private information that is broadcast. And private here means that transmitter 1, receiver 1 is the only one that wants it. Private here means transmitter 2, receiver 2 is the only one that wants it. Okay, once we have our message split, and all these U's are the random variables that are going to encode it, right? Next step is I'm going to use a superposition coding technique. Very standard in information theoretic achievability proofs. And basically, but this is a very non-standard way of representing it. So let's see what this means. I want you to sort of think of this as a 3D object, okay, where the biggest layer is the lowest layer of your mountain, and it's sort of coming up at you, right? So these guys are the two tops. Okay, and what this means is that I'm superimposing these top ones on all the stuff that's below it. Okay, so what does this mean? In my achievability proof, I'm going to generate random code books, as is standard, according to the following distribution. So I'm going to generate PU2, then I'm going to generate PU2PA given U2C. And that's the superposition aspect, right? Is that you generate your code books according to these conditional distributions. Okay, and then I'm going to generate X2 as a function. X2 is, again, what he sends of these other two messages. Likewise, at receiver 1 now, I'm going to generate the common stuff conditional on this guy. Why can I do that? I'm at transmitter 1. I know transmitter 2's messages, so I know U2C, so I can do this. Okay. Generate another layer, another superposition layer. Generate another superposition layer. Why is this one not encoded in X2? Because this U2B, 2PB, was message from user 2 that's private, but that is broadcast from user 1. So that's why it's not contained in the X2. It's only transmitted by X1. And then I generate X1 that's conditional on everything. Okay, great. That's fine. Superposition encoding is shown to be optimal in certain types of channels. For example, the degraded broadcast channel. So this is one of the reasons why we want to use it. Last element of my achievability scheme is Gelfand-Pinsker binning. And that's what these circles denote. Gelfand-Pinsker binning is basically dirty paper coding. Okay, and that's what I'm going to talk to you about. So what this dot here means is that 1PB is binned against 2PA. What does this mean? Let's look at it from the perspective of transmitter 1, receiver 1 channel only. Okay? Since transmitter 1 knows the message of transmitter 2, he knows U2PA. So he's able to code in a way that exploits this knowledge. And how he does so is by this binning. What Gelfand-Pinsker showed in the 80s is that the capacity of this channel, if you're looking only from transmitter 1 to receiver 1, this point-to-point channel, where one transmitter has non-causal knowledge of the interference scene, is given by the following. I'm not going to go too much into that. Suffice to say that in Gaussian noise, this becomes the dirty paper coding result, which is a celebrated result and was recently shown to be capacity achieving in the broadcast channel. So what this means in Gaussian noise, this binning, this random binning, is that this channel, where you have a transmitter, a receiver, and some non-causally known interference at the transmitter, is equivalent to a channel without any interference whatsoever. This is a quite powerful statement, right? It means that even if you don't know the interference at the receiver, it's enough to know it at the transmitter to be able to code around it. Okay, so Gelfand-Pinsker binning is dirty paper coding in Gaussian noise. And dirty paper coding is can be explained as follows. The name, of course, is very catchy, and the reason it's called the following is that, let's say I want to transmit some message, right? And here's my dirty paper. So if I just transmitted my message as I was transmitting it before, it doesn't get across. But if I adjust my ink to the dirty paper, you can see what I mean to say, right? Same thing, you can see this in the lattice code as well, but I'll just skip that for now. Okay, and so basically dirty paper coding result says if the interference is known non-causally at the transmitter, then it's equivalent to a channel without interference. So this is exactly what we're doing. This kind of dirty paper coding, all these circles mean who bins against who. And there's reasons why this is the particular binning structure, but I won't get into that. So basically our region, with all those different components, boils down to the following. I don't expect you to understand really what this all means necessarily. The primes are binning rates. All of these are sort of the rate splits. But we've shown analytically that this is the largest known region and reduces to capacity whenever capacity is known. One of the hard parts in deriving such a region, I guess, is that, yeah, we have this great region, it looks complicated and things, but what's really hard is how to pick these random variables in practice. Okay? And that's what we hope to do in some of the channels that I'll be talking about next. So it reduces to capacity whenever capacity is known. I think I'll skip over these. And what I'm going to be talking about mostly is two simpler examples to show you what this non-causal message information really means in terms of capacity regions. So the first region where we actually recently showed capacity is the high SNR deterministic approximation channel. What is this channel? So we have a Gaussian noise channel. This is the Gaussian noise cognitive interference channel that we were talking about before. At high SNR, this noise sort of goes away, and you can view this channel as a set of bit pipes. This is what these gray lines are supposed to mean. This is N11 bits, N21 bits, N12 bits, N22 bits, where all that happens at the receiver is that they get summed modulo 2, these bits. Okay. This is a recent technique that has been used to solve many multi-user information theory models. It's called high SNR deterministic models, introduced by Devroye et al. And the main idea is that by going from the Gaussian channel to this deterministic channel, and you can solve that deterministic channel more easily, then translate the intuition, the insight from that deterministic model back into the Gaussian regime and obtain constant gap results, meaning constant number of bits from capacity in the Gaussian regime. Okay. So we did we made the following high SNR linear deterministic model for the cognitive interference channel, which basically boils down to the following picture, right? If you want to let's look at, this is transmitter 1. If this is N11 bits, then that means that these N11 bits are received above the noise floor at the receiver. Here, these N22, these remaining bits, they get shifted down below the noise floor. I can explain this model to anyone who's interested later on, but this is sort of the Devroye model for the deterministic channels. And so we showed that capacity in this channel has a very nice form, much simpler than all those equations we were seeing before. Right? Rate for user 1 is bounded by N11. Of course. Why? Because X2 cannot help X1. Right? So that's why there is no N12 coming in there. That's where this asymmetry comes into play. So this guy can only hope to achieve as much communication as this link can support. R2, because of this asymmetric knowledge, can receive information both from the N21 link and the NT2 link. So that's what this is showing. This sum rate constraint says that, you know, this guy, he has to have some trade-off between sending information that way and sending information that way. And this is the trade-off right here. Whatever you don't transmit to that guy, you can transmit your own message on. So that's a very simple, intuitive explanation for it. And here you can see that this is a deterministic interference channel, deterministic cognitive one, where you have this one-way side information, two-way side information. Of course, the capacity regions get bigger and bigger as you increase the amount of side information. Okay, then the second result that we sort of use this to prove is this high SNR deterministic channel gives you intuition about the the Gaussian channel. Why do you need this intuition? If you don't have this intuition, you don't know how to pick all these mounds of random variables to achieve high rates. So solving this simple problem gives you what strategies do well, what kind of side information should I give in deriving my outer bounds. And so in this, in the Gaussian version of this channel now, these two regimes were known. These are, here I have A and B, so this is my interference links. And in different regimes, you want to do different things, basically. Certain regimes, weak interference capacity is known. Very strong interference capacity is known. But in this rest of it, capacity was previously unknown. And it still is unknown, but we were able to prove a finite gap. So here, these are the sort of gap from capacity that we were able to prove. And what's interesting is that these blue things, I'm not going to go into them, but they tell you how you should achieve it. Okay, so they give you, this coding scheme will achieve close to capacity in this regime and all that. So that's an interesting result. So again, this is sort of what we've, in the Gaussian noise, this is all what I've plotted. This is what all this previous stuff reduces to. Okay, extensions of cognition in multi-user information theory, there are many. Causal versus non-causal cognition. You can talk about cognitive relays. So here we have the gray ones you can always think of as primary users. What happens when you add a cognitive relay here, a cognitive relay here? This channel actually is being worked on currently by multiple groups, where you have an interference channel, but you have one cognitive relay sitting there in the middle. You know, you can think of a ton of scenarios where stuff like this would be relevant. And the question is, what is the capacity region of certain channels that look like this? If you add more cognitive users, more scenarios arise, you know, you can play all sorts of games and make all sorts of problems. The question is, which ones are relevant and which ones do you want to go after? Another aspect in which cognition has sort of come to light is in this degrees of freedom of wireless channels. Up to now, I've talked about capacity regions as the metric, the thing we were trying to optimize. Now, degrees of freedom is a different metric that has seen a lot of interest lately because it's such a simple one to understand. So the degrees of freedom in any kind of wireless channel, you can think of as the number of clean channels in a multi-stream network. So it's the number of parallel clean Gaussian channels, if you want, that can be simultaneously transmit. So degrees of freedom, for example, for an M antenna and receive MIMO channel is the minimum of the number of transmit and receive antennas, which I'm drawing with 2 each, degrees of freedom 2. Interestingly, interference channel, degrees of freedom is 1. Okay? This is a pity in some sense, okay? Because it means that, you know, by distributing the antennas, you're losing degrees of freedom. But if either the transmit side or the receive side antennas are together, have these infinite capacity links between them, you regain the degrees of freedom to the MIMO channel case. So, natural question is, cognition, what happens then? So if we have an M by M MIMO interference channel, degrees of freedom is M. Right? These M means the number of antennas. Here I've drawn 3 on each node. Okay, cognition. If you give these stars here are meant to represent the messages. Okay, so if you give one of this yellow message here to this transmitter, if you give it to this receiver, or you give it to this transmitter and this receiver, degrees of freedom remains m. But if you give different amounts of cognition, different messages to different users, you can regain the 2m degrees of freedom. So these are sort of results that have emerged recently. The other types of results that have emerged related to cognitive networks are scaling laws. So scaling laws describes how the capacity of this network scales as the number of nodes goes to infinity. Right? Started off by the work of Gupta and Kumar in 2000, right, where a kind of pessimistic result where the per node throughput is actually decreasing as the number of nodes increases. But more optimistic results using percolation theory arose, and then recently this idea of cooperation, having these kind of successive MIMO systems, you can achieve a constant per node throughput scaling. So the question is, well, what happens when you have cognitive devices in such networks? And so one of the few results on scaling laws with cognition is the following. It's a fairly simple extension of previous work. We guarantee that the primary nodes act as if the cognitive network does not exist. So this is an oblivious primary network. Okay, so these gray nodes do not know the blue ones exist, and they do not change any of their transmission parameters. Primary nodes, and our condition for the blue nodes to be allowed to transmit is that they don't affect the primary scaling law. Okay? If you affect the primary scaling law, that's not a viable scheme. So what we prove is that the primary users and the secondary users can both achieve the same scaling law as if none of the other networks was present, provided that the secondary network is more dense than the primary network. And this, of course, is the caveat that the secondary network has to be more dense. So essentially what you get is the secondary network being able to route around the primary network without any kind of penalty being paid. And with that, I hope that this has given you a sort of a tour of what cognition from an information theoretic perspective has meant. It's meant non-causal, or we have modeled it as non-causal message knowledge at certain one of the transmitters. And I've primarily focused on this simple kind of multi-user channels where you have cognition at some of the nodes, i.e. at the primary, at the secondary transmitter. And with that, I'd like to thank you and ask if you have any questions.
Question. Okay, Natasha, you skip over this dirty paper stuff.
Yeah.
These 2 slides. Can you explain this to us?
The dirty paper stuff.
I'd like to understand it.
These ones?
Previous one, yes. Start with this and then...
This one? Or the actual equation?
This one and the next one. This and the next one.
Okay. So the reason okay, so this was, Gelf and Pinsker have this result on discrete memoryless channels, okay? Meaning transmitters where we have non-causal knowledge of the interference that's going to be seen at the receiver. They solved the capacity region in discrete memoryless case. Costa in '83 said, well, what happens in the Gaussian noise channel? Okay. So Costa said, oh, let's pick a particular input distribution for the, can I use this maybe? Okay, so. I'm only going to say this because I can, yeah. So here we have U, X, Y, S known here and going to be interfering here. Okay. So this is the classical formulation. We have not interference that's going to be coming there known here. Capacity is that. And so Costa said, well, how about we pick U in a certain way? Okay. And it turned out that if you picked U in a certain way, you could optimize a certain parameter, and you would get the interference-free capacity out of there. And so that's known as the Costa's pre-coding coefficient. But so the reason why he called it dirty paper coding, I think, was I'm not sure why. I mean, it's pretty catchy. Well, you want to transmit a certain message, but you have dirty paper. So if you were to transmit it just as you would have before, you wouldn't get the message across. But if you do adjust your ink, so to speak, and this adjusting the ink is using this interference to your power rather than trying to subtract it off. And that's what the next slides are going to be about. You can get the message across. So dirty paper coding can be achieved by lattice codes. And this is kind of an example of a lattice code. So let's say you want to send 2 bits, right? So one of these 4 colors. Then this is what your receiver is going to see. So let's say you're power limited. So that's the interesting case in the Gaussian noise, right? If you have infinite power, who cares? So you have to be power limited. And let's say your interference is out there. So even if your transmitter knows this interference, it cannot possibly subtract it because it doesn't have enough power to do that. So the idea is, how do I still deal with this interference, and how can I achieve full capacity without, in the presence of this interference, which I know. So how do I send 0, 1? So now you can sort of see where this is going, right? If you send something that lies within this circle, so you satisfy your power constraint, but such that the addition of that and your interference brings you to the desired, right, 2 bits, then you're going to be fine. So it's sort of like a modulo lattice coding scheme that is a nice example of how this would work in practice. Same thing, this is just the same idea here. Don't know if that satisfies it. Yeah, okay.
Mike, what's the relation of this with what is called wet paper codes?
Wet paper codes?
Yeah, there's a whole bunch of papers with titles of wet paper codes.
I don't know the wet papers. I know some other no, I don't know. I forgot the name of the other ones, but I don't know the wet one. Do you have any other?
Well, I saw a lot of wet ones, but I never saw dirty ones. So this
I see. Well, then we should talk, because yeah. Okay. Yeah. I don't know what wet paper codes is.
Anybody else? Okay.
Sure.
I'm very interested in your work, and I'm sorry I came late.
Okay.
Some of your work can be used for the DARPA Cyber Genome Project.
Cyber Genome Project?
Yeah.
I don't know what this project is.
This is a huge thing right now.
Okay.
I can tell you. But basically what they're looking for is if there are some attacks and some malicious activity, you can use the information to figure out where it started from and where it's going.
Okay.
And I was going to talk to Wojtek about this thing, but there's something that...
Okay, well, we should definitely talk then, because I don't see the relation immediately. But okay.
Another thing that I know, this is of great interest to Air Force, actually, cognitive networks.
Oh, yes. This I'm aware of. Yeah.
We wrote a paper, I'm just trying to let you know.
Yeah.
That this is a protocol for routing between source and the destination in ad hoc wireless network.
Okay.
Which uses the idea of congestion and interference rather than the shortest route.
Oh, I see. So,
yeah. Your work is very relevant in that also.
Oh, excellent. Yeah, so this is, cognitive networks is a much bigger field than what I've sort of presented it as. There's a whole community out there that approaches it from a different perspective. That approaches it from a white space filling perspective, the first kind of slides I've talked about, and more protocol oriented rather than bounds on capacity regions. But so I just want you to be aware that this is a skewed view of this subject. But yeah.
So if you don't have enough time today, we'd like to invite you again.
Okay, sure. Great. Yeah, please. Come to Chicago.
Any other questions? Okay, let's say Natasha.
Okay, thank you.